In this section, we will examine how Birch-Mumaghan equation of state is meaningful. As I mentioned previously, the Birch-Mumaghan equation of state is the most frequently used equation of state in geophysics and also high-pressure physics and chemistry. Therefore, it may have special meaning, physical meaning, compared to other equations of state. There are two assumptions to build Birch-Mumaghan's equation of state. One is compression is expressed by a state not before but after compression as a reference. The second point is discussion starts from the change in squared length by compression. We will examine whether the equation of state built based on these assumptions have a special meaning or not in this section. In the first part, let us argue the significance of the Eulerian scheme. The Eulerian scheme is such that the volume before compression V0 is described by volume after compression V. The thermodynamic parameters under compression is expressed using V0 over V. Why this is useful is when volume goes to 0, pressure goes to infinite. This situation is easy to describe because the V0 over V goes to infinite as well. Here, let us construct the equation of state under the Lagrangian scheme. The Lagrangian scheme is such that the volume after compression V is described by volume before compression V0. Then thermodynamic parameters under compression is expressed by V over V0. As we defined the Eulerian finite strain to introduce the Birch-Mumaghan equation of state, let us define the Lagrangian finite strain in this section. Let us consider a cube with edge length L0 in an unstrained state. So this blue cube is cube before compression, and its volume V0 is equal to L0 cubed. Then we uniformly compress this cube to edge length L0. Then volume is V, which is equal to L cubed. Then displacement delta L0 is L equal L0 plus delta L. Then change in squared edge length is L squared minus L0 squared equal L0 plus delta L squared minus L0 squared equal to L0 delta L plus delta L squared. Here L squared comes first and L0 squared comes later because L0 is reference state in the Lagrangian scheme, and the change in squared length is expressed using L0, equation 4.5.4, and we consider the strain should be proportional to the edge length before compression. Delta L is equal to CL times L0, equation 4.5.5. Then we substitute equation 4.5.5 delta L equal CL L0 to equation 4.5.4 L squared minus L0 squared equal to L0 delta L plus delta L squared. Then L squared minus L0 squared is equal to 2L0 CL L0 plus CL L0 squared, then 2 times CL plus CL squared times L0 squared. Then we define the Lagrangian finite strain as minus 1 over 2 CL squared minus CL, equation 4.5.7. Then we express the Lagrangian finite strain using the volume compression. L0 squared minus L0 L squared minus L0 squared is equal to minus 2FL L0 squared. Then L0 L squared over L0 squared is equal to 1 minus 2 FL. Then L over L0 is equal to 1 over 2 power of L 1 minus 2 FL. Then volume is length cubed. Therefore, V over V0 is equal to L cubed over L0 cubed, which is equal to 1 minus 3 over 2 power of 2 minus 1 minus 2 FL. Then FL is equal to 1 over 2 times 1 minus 2 over 3 power of V over V0. So the Lagrangian finite strain is expressed by volume compression, equation 4.5.8. Then we construct the equation of state based on the Lagrangian finite strain in the same way as the Birch-Mumaghan equation of state. In this lecture, we call this equation of state Lagrangian equation of state. So let us come back to the definition of the pressure in the thermodynamics. Pressure is equal to minus the partial derivative of Helmholtz free energy with respect to volume V at constant temperature T, equation 4.1.1. And as was in the Birch-Mumaghan equation of state, the increase of Helmholtz free energy is assumed to be proportional to the squared finite strain with a volume decrease. The difference is this finite strain is not Eulerian but Lagrangian. So delta F is approximated by A times FL squared. A is constant. Then we obtain the volume derivative of finite Helmholtz free energy F as the partial derivative of Helmholtz free energy F with respect to volume V at constant temperature T is equal to the partial derivative of A times FL Lagrangian finite strain squared with respect to volume at constant temperature T, which is equal to 2A FL, the partial derivative of finite strain Lagrangian finite strain FL with respect to volume V at constant temperature T. Therefore, pressure is equal minus 2A Lagrangian finite strain times the partial derivative of Lagrangian finite strain with respect to volume at constant temperature T, equation 4.5.10. So we defined the Lagrangian finite strain as 1 over 2 times 1 minus 2 over 3 power of V over V0. Therefore, the partial derivative of the Lagrangian finite strain FL with respect to volume V at constant temperature T is equal to minus 1 over 3V times minus 1 over 3 power of V over V0, equation 4.5.13. As a result, the second order Lagrangian equation of state is minus p equal minus 2a the partial derivative of Lagrangian finite strain FL with respect to volume V at constant temperature T as equation 4.5.10. Then A is replaced by 9 over 2 KT0 times V0. The constant A is identical between the finite Eulerian and Lagrangian finite strains, and FL is 1 over 2 times 1 minus 2 over 3 power of V over V0, and the partial derivative of FL with respect to volume is minus 1 over 3 V0 times minus 1 over 3 power of V over V0. Then we simplify this formula. Then we have P equal 3 over 2 times the isothermal bulk modulus KT0 times minus 1 over 3 power of V over V0 minus 1 over 3 power of V over V0. If we use V0 over V as the Eulerian equation of state, the Lagrangian equation of state is 3 over 2 times the isothermal bulk modulus at 0 pressure KT0 times 1 over 3 power of V0 over V minus 1 over 3 power of V0 over V. Equation 4.5.14. So compared to Birch-Mumaghan equation of state, equation 4.2.13, the power of V0 over V is different. In the case of Lagrangian, it is 1 over 3 and minus 1 over 3, and in the case of Birch-Mumaghan equation state, it is 7 over 3 and 5 over 3. Thus, the power of V0 over V is by 2 different. Equation 4.2.2 different. Let us compare the equation of state based on the Eulerian and Lagrangian finite strains. This diagram shows the pressure and as a function of V over V0 of MgO, whose isothermal bulk modulus at 0 pressure is 160.64 GPa. A red curve shows the Birch-Mumaghan equation of state, namely the equation of state based on the Eulerian finite strain. And green one is Murnaghan's equation of state, and light green one is equation of state based on the KT's constant. And this blue curve on the light green curve is Lagrangian pressures given by Lagrangian equation of state. As you can see, the pressure given by Lagrangian equation of state is much lower than Birch-Mumaghan equation of state, namely the equation of state based on the Eulerian finite strain. And the equation of state based on the Lagrangian finite strain is almost identical to the equation of state based on the definition of isothermal bulk modulus without considering the increase of isothermal bulk modulus with pressure. The reason is clear. The Lagrangian finite strain does not increase dramatically with compression, in contrast to the Eulerian finite strain. So this diagram shows a finite strain as a function V over V0. Red one is Eulerian finite strain, and blue one is Lagrangian finite strain. Because Lagrangian finite strain is a function of V over V0, then it is almost linearly increases with increase in V over V0. In contrast, the parameter of Eulerian finite strain is V0 over V. Therefore, it rapidly increases at a high compression. This situation is even more clear in the case of the volume derivative of finite strain. So the volume derivative of a finite strain is almost constant in Lagrangian finite strain. In contrast, the volume derivative of finite strain rapidly increases in the case of the Eulerian scheme. This is the reason why the Birch-Mumaghan equation of state shows a higher pressure than Lagrangian's equation of state. Next, let us consider third-order equation of state in the Lagrangian and Eulerian scheme. The derivation of the third-order Lagrangian equation of state is almost identical to that of the Eulerian equation of state, namely the Birch-Mumaghan equation of state. The only difference is the difference of the definition of the finite strain. The derivation is very tedious, therefore let me just show the results. So third-order Lagrangian equation of state is pressure P is equal to 3 over 2 times the isothermal bulk modulus KT0 times minus 1 over 3 power of V over V0 minus 1 over 3 power of V over V0 times 1 plus 3 over 4 KT0 prime, the pressure derivative of the isothermal bulk modulus at zero pressure, times 1 minus 2 over 3 power of V over V0. So this is Eulerian third-order equation of state, namely the third-order Birch-Mumaghan equation of state. By comparing these two equations of state, you can find again the exponent of first V over, in the Eulerian parameter is V0 over V, but in Lagrangian parameter is V over V0, and the power is minus 1 over 3 and 1 over 3 in the Lagrangian. In the Eulerian, it's 7 over 3 and 5 over 3. They are the same as second-order equation of state. The difference, especially for the third-order equation of state, is the factor in front of the this finite strain factor is just KT0 prime. This is in contrast to the third-order Eulerian equation of state, which is KT0 prime minus 4. And again, this means the third-order Eulerian Birch-Mumaghan equation of state includes is become identical when KT0 prime minus 4 is 0, namely KT0 prime is 4. Therefore, the Birch-Mumaghan equation of state, or the Eulerian equation of state already includes the increase of isothermal bulk modulus, and the rate is kt0 prime is 4. In contrast, the second order, the third order about Lagrangian equation of state becomes identical when kt0 prime become identical to the second order large equation of state when kt0 equals 0. Therefore, second order equation of state does not include the increase of kt0, the isothermal bulk modulus, with increasing pressure. This is the reason why the second order Lagrangian equation of state gives almost identical pressure to the equation of state, integrating the definition of the isothermal bulk modulus with constant values kt0. So in both cases, the kt0 is assumed constant. Then let us compare the Lagrangian and Eulerian equation of state up to third order. So in both cases, the material is gold. Therefore, the k prime is larger than 4. Therefore, third order Birch-Mumaghan equation of state gives larger pressure values than second order Eulerian equation of state. The third order Lagrangian equation of state, of course, gives a larger pressure values than second order Lagrangian equation of state, because the second order Lagrangian equation of state is identical to the third order Lagrangian equation of state with kt0 prime. The pressure derivative is 0. But the increasing difference between third order and second order in Lagrangian is much smaller compared to Eulerian, even though second order Eulerian already includes the effect of the K0 increase with pressure. So the difference becomes larger and larger with increasing compression, means decreasing volume. Then next, let us consider fourth order equation of state. This is a fourth order Lagrangian equation of state. This is fourth order Eulerian equation of state. Again, the feature of the difference is almost the same as third order and second order. This term, special for the fourth order, is different. The factors are different, like this and like this. So let us compare the fourth equation of state of the Lagrangian and the Eulerian scheme up to fourth order. So this is the material is NaCl, sodium chloride. K0 is 23.7, K0 prime is 5.14, and K0 double prime is minus 392. You can see the fourth order Eulerian equation of state gives a bit smaller pressure than third order. In contrast, the fourth order gives significantly higher pressure than third order equation of state. And important point is the K double prime is minus, therefore K K0 prime decreases with increasing pressure, namely the rate of the increase of K0 with pressure is decreasing. Nevertheless, the log pressures given by fourth order equation of state is significantly higher than third order. So this is quite strange phenomena, and more importantly, the difference between fourth order and third orders are very small, so the equation of state converges even if we obtain higher degree of higher pressure derivative of bulk modulus. It is an improvement of the accuracy of the pressure is small in the case of the Eulerian equation of state. In contrast, in the Lagrangian equation of state, the pressure increase from third order to fourth order is even larger than second order to third order. Therefore, we need a very high derivative, volume pressure derivative of bulk modulus to obtain accurate pressure using Lagrangian equation of state. I don't confirm, but I expect fourth order equation, higher order Lagrangian and Eulerian equation of state will converge at very high order of equation of state. But I think it is impractical to obtain such high order of bulk pressure derivative or bulk modulus. And this diagram indicates that the Eulerian Birch-Mumaghan equation of state converges much rapidly compared to Lagrangian. Therefore, Eulerian equation of state, namely Birch-Mumaghan equation of state, should provide more accurate pressures than Lagrangian equation of state. So this is the reason why we choose Lagrangian schemes rather than this is the reason why we choose the Eulerian scheme rather than Lagrangian scheme to obtain more accurate equation of state with lower order of pressure derivative of bulk modulus. Then next question is, why are we consider the expansion of squared length to construct the equation of state? When we define the Eulerian finite strain, we started the argument from the change in squared length of the body. Honestly, I don't understand the reason. I have no idea why the expansion of a squared length is essential. Therefore, let us construct equation of state with a different definition of the Eulerian finite strain. One is starting from the expansion of cubed length. Because we consider the volume compression, this would be a more natural scheme. Another choice is we consider the linear length. This should be a simpler scheme. Therefore, we should be able to obtain not too bad equation of state by adopting expansion of the cubed length or linear length. Then we derive the equation of state based on the Eulerian finite strain starting from these expansion, and compare three equation state. So let us consider the Eulerian finite strain from the cubed length. So the difference in the cubed length is L0 cubed minus L cubed. The definition is the same as before. The L is a length, L0 is the length of the body before compression, and L is the length of the body after compression, and V0 is volume of the body before compression, and V is volume of the body after compression, and delta L is a length in change in length by compression. So L0 cubed minus L cubed is equal to minus L squared delta L plus 3L delta L squared minus delta L cubed, equation 4417. As is before, delta L is proportional to the length, and because of the Eulerian scheme, this is defined as a proportional to the length after compression. Then we substituting this definition, this relation to equation 4417, then we have L0 cubed minus L cubed is equal to minus 3CE, C is this factor, plus 3CE squared minus CE3 cubed times L cubed. Then we define new finite strain as FE3 equal to minus CE plus CE squared minus 1 over 3 CE cubed, equation 4419. Then according to the Eulerian scheme, we have FE3 is equal to 1 over 3 times V0 over V minus 1. Because of cubed here, V0 over V does not have strange power. So equation 4.5.22. And volume derivative of a finite strain of the Eulerian finite strain starting from a cubed length is minus 1 over 3V times V0 over V squared. Then as is before, we construct the second order and third order Birch-Mumaghan equation state. The discussion derivation is almost identical to the previous examples. Then the results are the pressure is equal to the isothermal bulk modulus at 0 pressure, KT0 times V0 over V cubed minus V0 over V squared, equation 4.5.24. And similarly, third order equation state is pressure equal KT0 times V0 over V cubed minus V0 over V squared times 1 plus 1 over 2 power of KT0 prime minus 5 times V0 over V minus 1, equation 4.5.25. Then next, let us consider the Eulerian equation set from a linear length. So symbols are the same. Here we simply consider the difference of the length before and after compression, which is equal to minus CE1L. So we define new finite strain. F finite strain E1 is equal to minus CE1. Equation 4.5.28. CE1 is ratio of change in the length relative to the final length. Then we construct the equation finite strain. New finite strain is expressed using the volume compression V0 over V as 1 over 3 power of V0 over V minus 1. Equation 4.5.31. And volume derivative of finite strain is minus 1 over 3 V4 times 4 over 3 power of V0 over V. Equation 4.5.32. Then with the same derivation, we have second order and third order Eulerian equation of state from a linear length. Then which is pressure is equal to 3 times the isothermal bulk modulus at zero pressure KT0 times 5 over 3 power of V0 over V minus 4 over 3 power of V0 over V. 4.5.33. And the third order equation of state is P is equal 3 times KT0 times 5 over 3 power of V0 over V minus 4 over 3 power of V0 over V times 1 plus 3 over 2 times KT0 prime minus 3 times V0 over V 1 over 3 power of V0 over V minus 1 unity. 4.5.34. So let us compare the Eulerian equation of state based on the linear difference of the linear length and squared length and cubed length. The finite strain is defined, the defined finite strains as follows. So the factor of these red part are different among these three cases. So here factor is 1, factor is 1 over 2, 1 over 3, and V0 power of the V0 over V is 1 over 3 in a linear case, 2 over 3 in squared case, and 3 over 3 for the cubed case. And pressure derivatives are like this, and this 1 over minus 3 V0 are the same, but the power of the V0 over V are different, 4 over 3, 5 over 3, and 6 over 3. And second order equation of state are something like, so KT 3 times KT0 is identical. The power over V0 over V's are different, 5 over 3 and 4 over 3 for linear case, 7 over 3 and 5 over 3 for squared case, and 9 over 3 and 6 over 3 for cubed case. And third order equation of state, the former factors the first factor is different, linear case 3 over 1, squared case 3 over 2, and cubed case 3 over 3. This part is the same, and this part is identical to the definition of the finite strain, and major difference is in the case of linear, this factor is KT0 prime minus 3, KT0 minus 4 for squared, we have already learned, and KT0 prime minus 5 in the case of cubed. So the most essential difference among these three equations of state is the third order equation of states become identical to the second order equation of state when kt0 is equal to 3 for the linear case, 4 for the squared case, and 5 for cubed case. The Birch-Mumaghan equation of state was justified because many materials were considered to have kt0 prime equals 4. However, if this is the reason for this justification, if the material have a kt0 prime equals 5, cubed expansion should be more appropriate. Actually, we have already seen gold have a k prime more than 5. Therefore, along this justification, the cubed expanded equation of state should be more appropriate for material like gold. Then let us consider the three Eulerian equation of state using the experimental data. So this is a shock compression data of MGO. We will learn shock compression in the later section, and in the shock compression temperature increase, therefore we have to consider temperature effect. I will discuss thermal equation of state in the next section. In any way, we fit the equation shock compression data to the first power and second power and third power Eulerian equation of state. And we obtain the parameters like this. So the V0 is a volume before compression, KT0 is the isothermal bulk modulus, of course, and KT0 prime is pressure derivative of the isothermal bulk modulus. You can see these three equations of state gives almost the same parameters. So there is no difference among difference powers of the Eulerian equation of state. Therefore, the expansion of the squared length to obtain Birch-Mumaghan equation of state has no physical meaning. Finally, let us come back to the comparison of the Eulerian and the Lagrangian schemes. These red curve is fitting by the Eulerian equation of state, and this blue is the best fitting of the equation of state to the Lagrangian scheme. These parameters are parameters for the thermal equation of state. Even if we change these parameters, it is impossible to fit Lagrangian equation of state to the shock compression data. Therefore, Lagrangian scheme cannot reproduce shock compression data. Therefore, here using the experimental data, we can conclude the Eulerian scheme is better than Lagrangian scheme. So these are conclusions of this section. The Eulerian scheme is better than the Lagrangian scheme to build equation of state to reproduce experimental data with fewer and lower orders of bulk moduli. The expansion of a squared length to define the Eulerian finite strength does not have a special physical meaning. So this is the end of the section 4, examination of the Birch-Mumaghan equation of state.